Okay guys, 3.4 is all about kind of an extension on 3.3 in some ways, but also about how we take that information that we got and graph functions. There's a few different things that we can do to facilitate graphing from 3.3. Before that, let's just talk about parent functions. For any polynomial, the parent function is x to the n, where n is just the power of the largest degree. When n is odd, the domain and range are both from negative infinity to infinity because their n behaviors are opposite. However, when n is even, for the parent functions anyway, the domain is negative infinity to infinity, but the range is just 0 to infinity, and the function is decreasing from negative infinity to 0 and increasing from 0 to infinity. For the odd functions, it's increasing the whole time. Now, of course, both of these can be influenced by shifts and negative multipliers for a. But we talked about how to move like the square root functions and the absolute value functions in the past in quadratics, and so the same thing happens here. The multiplier in front can be a vertical stretch or shrink, a negative is a reflection, and h and k can move left, right, and up, down. The graph of a function f of x equals a times x minus h to the n power plus k receives both translations as well as a stretch and shrink from a. Of course, we like to do our stretch and shrinks when we're describing it before we do anything else. So when you get something like describe the transformations from the parent function for x to the fifth minus 2, well, the parent function here is x to the fifth, so it's really just the minus 2 portion. All you do is down 2 to get x to the fifth minus 2. Pretty simple. For x plus 1 to the sixth, for a parent of x to the sixth, you go left 1 to get x plus 1 to the sixth. Okay, so let's describe one that actually has more things going on. Our parent is x to the fourth here. We have a vertical reflection, which is our negative. We have a vertical stretch by a factor of 2, negative 2x to the fourth. Then we have our shifts, so right 3, up 5 to get negative 2 times x minus 3 to the fourth plus 5. So this is all similar to the way it's been in the past. So it shouldn't be too surprising or something too new. So let's talk about how graphs behave at 0. So we know that multiplicity determines how many times a 0 has, and how the graph behaves at the 0 is entirely dependent on the multiplicity. There's kind of 3 different options: multiplicity 1, multiplicity even, and multiplicity odd greater than 1. So if it has multiplicity 1, this is where it crosses normally. I like to think of it as like crossing a river. If you cross the river one time, you just keep going. Multiplicity 2. If you cross the river twice, you go and you come back. So it kind of, if you changed your mind in the middle of the river, it has an effect of bounces. So if we look at just with the x plus 2, what it looks like from this equation, that's just a 0 at negative 2. It just crosses normally. It does whatever the graph was doing beforehand, and it just keeps going. Now, the x plus 1 squared, we know that this is a parabola. It comes down to negative 1, and it kind of bounces back off. So it kind of levels off at the 0, then turns around. Multiplicity 3. It levels off but crosses. If you were crossing a river 3 times and you couldn't make up your mind, if you made your choice, change your mind an odd number of times, you eventually do cross to the other side, but not before kind of leveling off and spending time making your decision. So the x minus 1 cubed portion of this, it kind of looks like this. We have that portion here. It kind of levels off, but kind of just behaves normally. So kind of like the x cubed function does. You know, it kind of looks like it goes somewhat flat in the middle, but it does eventually go up or down on either side. Now, for the most mathematical term you'll ever hear, turning points. A polynomial function of degree n has at most n minus 1 turning points, with at least one turning point between distinct zeros. The reason for that is if you have two zeros where you're crossing the axis, the only way for you to get back down to 0 is if you're going one direction, you have to turn around to go back down or turn around to go back up. Not super scientific. End behavior is what happens when the graph reaches very large positive and negative values for x, which is determined entirely by the degree of the function and the coefficient that goes with it. We have 4 options here for degree in A. Degree, the behavior based on degree is the even or odd. Either you have an even or odd power leading. Technically, there can be some other kinds of powers. We're not going to worry about those so much in terms of integer powers, so evens and odds. A can be positive or negative. That means 4 categories. Odd and a greater than 0, so the most basic example of this would be positive x cubed, which we know looks like this. So let's talk about what it's doing as it goes to the left and to the right. So as x goes to negative infinity, so as x is going to the left, our function f of x is going down, which is also to negative infinity. But as x is going to the right, to positive infinity, as we go right, our function is going up. F of x goes to positive infinity. So this is how you would write your end behavior. Your x is doing something left or right. Is your function going up or down? In some cases, it may not look like it's doing either, but if it's leveling off, that's also something that you would note. In all of our regular polynomial functions, that's not going to be an issue. What's the difference between that and negative x cubed? Well, we know a negative is a vertical reflection, so it takes this in, flips it. So instead it's going up on the left and down on the right. Since it reflects y values, our y values are represented by the f of x. It will change the sign of the f of x's. So as x goes to negative infinity, f of x should now go to positive infinity. Is that represented here? As x goes to the left, is y going up? Yes. As x goes to positive infinity, f of x goes to negative infinity. As x goes to the right, is y going down? Yes. Now the same thing can be applied to even. We have x squared and negative x squared. We know what the parabola looks like. Goes up on both sides. So if we're going to do the end behavior here, it's as x goes to negative infinity. On the left, it's going up, so f of x goes to positive infinity. And as x goes to positive infinity, f of x goes to positive infinity. So the difference between evens and odds primarily is that evens are always going to the same direction on both sides. Because remember that if you raise something to an even power, both negatives and positives become positive. So the only thing that can really influence that is the a in front of it, and the a is going to do the same thing to both terms. So the negative x squared is the downward facing parabola. And again, it switches the y values. So as x goes to the negative infinity, f of x goes to negative infinity. As x goes to positive infinity, f of x is going to negative infinity. Because again, even functions, even powers, do the same thing on both ends. And we'll use some applications of this on the next video.